Good morning, Matt.
Good morning, Michael. What have we got on tap today?
We want to talk about inverse functions.
Well, let it roll. Let's see. What do you mean by an inverse function? Like 1 over x is the inverse of x, or
Well,
what?
I would call the reciprocal, but what we want to do is something that a function, it takes a value like x, turns it into something y, and then we want to take that y and turn it back into x.
So we want to go back to where we started from.
So we can draw a little picture, like we have this value x, and somehow it changes into a function, into a value y, and there's a function. Should I call it g, or should I call it f?
You pick it.
I'm going to pick g just for fun, and then we want another function that goes backwards,
You'll call that f.
f. Okay, so g of x would equal to y, and f of y is equal to x. So for instance, if I give you a number like, I don't know, why don't you give me a number?
2.
Okay, I'm going to multiply by 2 and get 4.
4.
Now if I give you 4, how do you turn it back into 2?
You have to divide.
You have to divide by 2.
Yeah.
So maybe I can show you a picture of this, because we love our charts.
Let's have a look.
Here's our little chart. And so here's a graph with an x, and we double it. And of course, we know we can plot graphs, so the function that takes x and multiplies by 2 gives me a straight line, y is equal to 2x, and I get this little straight line, like that.
Right.
Now, what you did is you did the opposite. You took my number 2x, see you have it over here, and divide by 2, we get back to x.
Yeah, so what happened was the 2x here becomes the abscissa here, and then at half x, you get half of 2x, which half of 2 is 1, so we should be 1 down here, which is what we started from.
Exactly. And we can do a little bit of algebra. Here we have this equation y is equal to 2x. Say, well, if I take the 2 and bring it over to the other side, I would have a half y is equal to x, which is the graph of this picture here.
Oh, so if once we have the equation, say, going in one direction, we just have to rearrange it so x is a function of y.
Right, exactly. Now, graphically, it looks kind of interesting. You can see these two pictures kind of look like a mirror image of each other. Okay.
Yeah.
Another way to get this is by rotating the picture.
Well, do you have a picture of that?
Of course I do, Matt. You know how prepared I am. So here's a picture. We'll start again with this original curve, y is equal to 2x right there. Okay. And I've drawn this diagonal line, which you notice passes through all my grid points. So this is the point y is equal to x. So here's the x-axis, and here's the y-axis. Okay? Now, to get the inverse function, I'm going to switch the roles of y and x. And I have a very cute animation that lets me rotate the x into the y. We just rotate the axis. The diagonal line stays the same because that's y is equal to x. Now we get this new line, like we had before, x is equal to 1/2 y.
Now, when you look at that line, the new one, x equals half y, and the original one, y equals 2x, what is the relationship between, like you did a 360 rotation about an axis centered on the dashed blue line?
Yeah, it's a very interesting thing. Well, first of all, because it's just a rotation, lines go to lines.
Yeah.
So it stays a line. These lines pass through the origin, so the origin stayed the same, so they all pass through the origin. But something else changes. Okay, so we get a different line. It's a line going through the origin. But we notice the slope is exactly 1 over the slope of this guy. This was slope of 2. This is the slope of 1 over 2.
Well, can you go back to the previous slide? With
Sure.
Y equals 2x, or that one?
Now, okay.
So what I'm thinking is, what happens, it's kind of hard to draw here. Maybe we could draw the line y equals x starting here, and then aren't we just reflecting it around that line?
That's basically a reflection. Now, in this picture, the reflection sort of seems to be along a vertical line. But if we instead reflect it along this line, this orange line would flop down over there. So it's a reflection across the diagonal.
Yeah, so
I showed it as a rotation because I like rotations, but you can also think of it exactly as a reflection across that line.
oh, and that might help us in drawing it.
Exactly.
Oh, let's see if that eventually happens.
So here we go. We rotate this. Oh, I've already rotated, right? So the original line was back here. And you sort of go, okay, well, can I show you the original line?
Yeah, go back to the original.
Here's my original line. If I reflected this line across this, you say, okay, this is a mirror. So of course they would touch here, and then the reflection would go here.
Yeah, basically stick a mirror along y equals x
Exactly.
and reflect the line, and that would be the image in the mirror.
Now, of course, mirrors can reflect more complicated things, so can I show you a more complicated function?
Yeah, let's try something a little more interesting. Oh, that looks very much more complicated.
So here we go. I'm going to actually show you what I call the function. Y is equal to 2x cubed. So it's a cubic function. That means for positive values, it goes up fairly quickly. For negative values, it goes down fairly quickly. It flattens out at x equal to 0. That's my little cubic. And I put in some 2's in here so it wasn't a boring 1's all the time. But you see the value 1 here. If I cube it, I get 1. And when I multiply it by 2, I get here. So the point 1 maps to the point 2.
2, right.
And I can actually do the algebra. If I took this curve and say, how can I solve for x in terms of y? Well, I say I take the 2 and put it underneath the y. That gives me a y over 2. Then take the cube root of both sides. I end up with this formula. X is the cube root of y over 2.
What does it look like?
What does it look like? Well, I wish I could do a reflection for you, but I'll do a rotation for you, Matt.
Oh,
So
wow.
here we rotate,
Oh, and there it is.
and this is what the cube goes. Now, what you notice is, of course, it grows much more slowly than the cubic. Has this sort of vertical slope at 0, which is kind of interesting. But it does exactly what we want for this inverse function. So remember, we had this function, took the value 1 and brought it to the value 2. If I start with 2 here, plug it into the curve, I get the value 1. So 2 goes back to 1. So it's exactly doing this little loop. 1 goes to 2, and 2 goes back to 1. So that's what we want our inverse function to
That's
do.
what we want it to do. So do you have any other examples?
I do, because there's some interesting complications. Not every function is invertible, but usually you can at least invert a piece of it. So you might say, why did Michael go to cubics? Well, because quadratics are a problem. And maybe you can see what the problem is going to be. Can you guess what the problem might be?
Well, I think there's a problem if you look at any level line, it cuts the function in 2 places.
Right.
So when we want to go from solving for x as a function of y, which place are we going to pick?
And that's exactly because quadratics have this problem. When you try to take a square root, you have to say, do I want the positive square root or do I want the negative
You
square
can
root?
show that too, right?
So let me rotate this. And of course, rotation doesn't know about functions. It just rotates the picture. And now we have this problem that if we take the value y equal 1, we don't know whether we should take this part of the curve or that part of the curve.
Well, let's get rid of the bottom half.
So let's get rid of the negative part, and there we have a nice little inverse.
So not everything's invertible, and it looks like if you look at this curve, it looks like anytime there's maybe a maximum or a minimum, you're going to see that behavior of the parabola locally.
Exactly, because if you have a little maximum, you're going to have 2 points that where the horizontal line passes through 2 points. That's a problem when you rotate it.
Sure, and we know there's a famous curve like that.
Let's take a function that has lots of maximum and minimums. So here's a friendly
Oh,
curve.
so you're going to see that right at this point here, when we go to the left, the right and left of it, again, it's like an upside down parabola, so you're going to have a problem near the maximum.
Exactly. So let's do the rotation and see exactly how this problem comes up. Now, of course, this is just the sine function, so I have it here. I'm pointing at your chest, but I'm actually pointing at this
Yeah, no, I see you in
equation.
the-
Yeah, there you go. And sine of x, and say we want to find the inverse function. We'll talk a little bit about that notation later, but this means the inverse function of sine. Sometimes if you're doing computer programming, it shows up as a sine. Other people call it arc sine. We'll call it the inverse of the sine function. So let's rotate.
Oh, and of course, we have to chop it off at the max and min.
At the max and min, so like there's a max here, there's a min there. That's going to be a problem. So we chop it off, and then we get this.
Yeah, and actually, you have to kind of turn your head sideways to look at it.
Yeah.
You're looking out on the computer because that's the first quadrant. It's still the first quadrant. It's just that you rewrite it, x would be horizontal. Now it's vertical because we got there just by rotating.
Right. So we have this interesting thing where the sine function we know maxed out at 1. So this is why the limit here is 1.
So that should be max is at pi by 2.
Pi by 2 is about
1.57, so almost
about right.
2/3, yep.
Yeah.
So it's maxed out in the right places.
And so that's the inverse function.
Fantastic. I think we can go forward with this.
Next time we'll talk about derivatives.
Fantastic.